Hello, welcome to the course Electronic System Design. Last lecture we saw one example where we have a complex combinational circuit which is using AND or NOT, this kind of gates, and we saw that we can write a Verilog code to implement this using HDL. We used simulation software iVerilog and generated the output using this software, which is both in terms of the truth table. This truth table what we generated using the simulation, that we cross verified using our hand calculated truth table which was matching, and then we saw that the waveforms, how the waveforms of this look like. We have 3 inputs and 1 output in that circuit. When we change the input parameters in digital form 0 1 0 1, and we see the waveforms are changing based on the applied input, and then we saw that there are intermediate values or intermediate wires which we are interconnecting these gates. These can also be saved, and which are very useful in cross verifying, or if there the circuit implemented has any problem, then these intermediate values are very important. We can go to individual gates and check the output whether it is giving the desired result. If not, then the problem is close to that particular wire. So, we saw one circuit last time. Today we are going to see one another circuit which is very important circuit in digital design, which is called the full adder. So, this adder is a circuit which take 2 inputs as a input argument, and one is the carry which comes from the previous state. So, altogether there are 3 input variables A, B and the carry from the previous stage, and this full adder is adding them up, these 2 inputs along with the carry, and generating the sum resultant of this sum, and there is a carry. If there is a carry formation, that carry input, the carry output will be generated using this full adder. So, let us see how we can implement full adder using Verilog language using these free softwares. So, we again go back to our bin directory there, where we want to make this Verilog code, and we open a file, a simple text document, let us say full adder, and we need to change the file extension also as .v instead of .txt. So, once we do it, it always gives a warning which we click yes, and this is the full adder file where we want to write the code. So, let us discuss first what is the full adder. So, we are going to discuss today the example which is full adder. So, as we said, this is going to generate the sum and carry from the inputs, 2 inputs A, B and the input carry in. So, the structure of this full adder is something like this. We have 2 input XOR gate where these 2 inputs are connected, A and B, and then we have AND gate. These 2 are connected to this as well. This is C in, or the input carry. This is a connection here, and this is the output sum, and here this is a OR gate. This is C out, which is the output carry. So here we have full adder which has two inputs A and B and the carry from the previous stage. These three are connected in such a way we use two XOR gate, two AND gate and one OR gate here. The output of this XOR gate is S, which is the sum, and the output of this OR gate is the C out, which is carry. So if we write the truth table, which is very well known for the full adder, we can write different vectors. So here we have three inputs A, B and C. It means we will have 8 lines in our truth table. So A, B and C, which is carry in, and at the output we will have sum and carry. This is our sum or S, and we have carry. So these are the two output for this full adder, and now we write all different combinations of A, B and C in. This is 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0 and then 1 1 1. These are all the possible 8 combinations for 3 inputs, and the values of sum and carry are: for 0 0 0 the sum is 0 and the carry is 0. For 0 0 1 sum is 1, carry is 0. For 0 1 0 sum is again 1, A and sum of A and B will be 0 and 1 is 1, carry is 0. When we add this A and B, the sum is 1, sum is 0 and the carry is 1. Next, for 1 0 0 sum is 1, carry is 0. For 1 0 1 sum is 0, carry is 1. For 1 1 0 sum is 0, carry is 1. And for 1 1 1 the sum is 1 and the carry is also 1. So this is the truth table of our full adder circuit, where we have two outputs, sum and carry. So now today we are going to implement this full adder using our Verilog language. So we go to the text editor and start writing the Verilog code. We start by writing module and we give it a name, full ladder, and then we start bracket where we want to specify the ports. So, here we can specify inside itself by writing input and output instead of writing A, B, C, sum and carry here and later declaring input and output. Here itself we can write input and output. So, this is input wire A, B and C in. C in is the carry input. Then we write output wire, which is sum and C out, the carry output, and then we close down this bracket. So, this is our instantiation of full adder module. We have written the statement module, full adder and the input output ports we have defined inside that itself. Next, we need to take now intermediate wires, because we are using intermediate wires. For example, one XOR output goes to the input of another XOR and to the AND gate. So, these are intermediate wires. If we count it, we are using actually these 5 intermediate wires. So, we need to define that as well. So, that we define by wire statement, and with this square brackets we are writing 4:1, 4:0 and then T. So, by this statement we are saying that we are defining wires by name T and the range is 4 to 0. It means we have T0, T1, T2, T3, T4. These are all the intermediate wires which we are going to use in our module. So, these are different wires. So, instead of writing wire T1, T2, T3, T4, we can in one statement specify that T is a wire which has width of 5 from 0 to 4. So, 0, 1, 2, 3, 4. Similarly, T0, T1, T3, T3, T4, T5, these are the wires which we are going to use in our design. So, these are the intermediate wires which we have defined. Now, we go back to our circuit which is shown on the right and start writing the code. So, the first one is the XOR gate where my two inputs A and B are going. So, let us write the code for this. So, we write XOR, this is the XOR gate and I give it a name, let us say X0. This XOR gate has two inputs and one output. So, we first write the output. The output to this, let us say, is T0. So, this I specify by this T0 and A comma B and then close. So, this statement means that there is a XOR gate which I am calling by the name X0. So, this is a X0 gate. This has two inputs, one output. Inputs are A and B and the output is T0. So, this wire which is intermediate wire, this wire name I am giving it T0. So, by this line XOR X0 T0 AB I have modeled this gate in HDL. Similarly, now I go to the second gate which is the XOR gate. So, I write XOR, I give the name as x1 and write sum t0 comma cin. By this statement, what I am doing, there is a XOR gate here. I am giving it a name x1. The name of this XOR is x1. The output of this is called sum. So, here this S I am calling it sum, and the input to this x1 gate is one is with this intermediate wire T0. So, I am writing here T0, this is the intermediate wire which is the input to this gate, and the other input is this C in. This C in also connected to this x1 gate. So, the two inputs are T0 and C in, and the output is sum. So, this is what I have written for this second gate. Similarly, for the third gate, I can write there is a AND gate I am writing and giving it a name, let us say A0, T1 comma A comma B. So, by this statement I am saying that there is a AND gate which is named as A0. This AND gate has two inputs A and B, and the output I am calling it by a already declared wire T1. So, this wire is actually I am naming it T1. So, this wire is the output of A0. So, we can write and let us give this gate a name A1 and then we start. So, this gate A1 now has output which is again a intermediate or internal node. So, let us give this internal node some name, let us say T2. So, we write here T2 which is the output of this gate, and then the one input is C in and the other input is T0 which is the internal connection. So, these are the pins for this gate which is AND gate named A1. We terminate the line here, and then we have this OR gate here. For this OR gate, the inputs are T1 and T2, both are internal connections, and the output is C out or C carry, whatever we want to call it. So, let us write the code for this. We write OR which is a OR gate, and let us give it the name some O1. The output is C out, we are calling. One input is T1 and the other input is T2. We close it and close the line. So, now we have put the statement for all the gates. We have 5 gates. So, we have 2 XOR gate, 2 AND gate and 1 OR gate. So, we have written code for everyone. Now, we AND this module. So, we do that by the keyword AND module. So, this is the code for full adder in Verilog, where we have implemented this digital circuit which is behaving like a full adder. It has 3 inputs A, B and carry, and it generates the sum of A and B and one carry output if it is there. So, once we write this module for full adder, now is the time to apply different variables like A, B and C values and generate the output. That we do by making a test bench. So, let us write a different Verilog program for test bench. So, the process is again same, we go for the bin directory and we make a new file full adder underscore tb, and the extension we need to change to .v. So, this is the test bench file. Let us edit it by notepad. Now, we need to write the test bench which is applying different values to this full adder. So, we start with our standard procedure which is module specification. So, we write module and we are writing a test bench for full adder. So, let us give it a name full adder underscore test bench, and it does not have any port, input or output port, because this is itself going to generate the signal and receive the signal. So, we do not have pin descriptions. However, we need to define the register values for all the inputs. So, let us say this is register A, B and C. These are the 3 registers we are assuming, and we have to assume wires for both of the outputs. So, we write wire, this is sum and this is carry. Now, we instantiate the previous module which we developed. So, this module we have given a name full adder. So, let us copy this name here and we call it here. So, we are instantiating this full adder here and giving it a name, let us say add 1. So, this is a name which I am giving to this. Now, I need to specify these register values to the internal pin mapping of this full adder. So, in the full adder we have 3 inputs which is A, B and C in. So, we write let us say dot A. So, this is the pin which is inside this full adder module, and we want to connect this to our local register AA. So, by writing this, whatever the signal AA is generating, that is passed to the pin A of the full adder. This is how we write dot A and then in the bracket the local register value. Similarly, to pin B we want to connect this register value BB. So, we write dot B and inside the bracket we write BB. So, whatever is the value at BB locally at register A, that will be passed to the pin B of the full adder, and similarly we write for dot C in, which is connected to locally C. Then we connect the sum to SS and C out to carry. So, this is how we have made the connection and now we close it here and terminate the line. So, this is our module instantiation where we are calling this full adder module, giving it a name add1 and mapping our local ports to the internal ports of that full adder. Now, we start with the initial statement. As we discussed, initial is the block which is executed once in a simulation. So, we start with initial, begin, and there will be end. So, this is the complete initial module. Inside this module, we are going to write the code. So, the code is nothing but the different vectors or the different values of A, B and C in which we are going to assume here. Those values will be applied to full adder module. So, at time t equal to 0, or we specify the time as hash 0, which is in 0 unit time, we want to apply the first row which is 0 0 0. It means A is 0, B is 0, C is 0. So, we will write AA as 1 tick B 0. So, one binary value of 0 will be applied to AA. Similarly, BB will be applied to 1 tick B0, and similarly CC will be applied 1 tick B0. So, this is one vector where we are applying 0 0 0 value to A, B and C. We can write it in 3 lines as well. Instead, we can just put a semicolon and keep writing in the same line. So, in this, instead of writing 3 lines for these 3 values, just like the earlier example, in this example we are writing in a single line. So, this is first vector. Similarly, let us say after a delay of 5 unit, we are writing the another vector which is AA is still 0, B is 0 and C is 1. So, we write A tick B 0, BB is 1 tick B 0 and C is 1 tick B 1. So, this is the vector where we are applying 0 0 1. Similarly, we generate all the values possible. Let us say after delay of 5 again, we are writing 1 tick B 0, BB equal to 1 tick B 0, and here we want to apply B as 1. So, 1 tick B 1 and CC equal to 1 tick B 0. So, this is 0 1 0. Next, we are applying AA equal to 1 tick B 0, BB equal to 1 tick B 1 and CC equal to 1 tick B 1. So, these are the initial 4 values which we have written here. We can copy the same thing, we paste it here. For the next line only the value of A is changed. So, we just change it to value 1. Now, this is the fifth line which is 100, then 101, 110 and 111. So, these are all the possible values of vectors A, B and C. Now, we write the AND statement which we have already put here. So, this is the initial statement where we have put all the values of variables A, B and C. Now, we initiate another initial block to monitor all these values. So, we write initial, begin and in between these we need to write $monitor. We want to monitor $time and A. This is the $monitor statement. We again start one more initial block to save the waveforms. We will write dump file. We give it a name, let us say full ladder .vcd and $dump vars. We write 0 because we want to store all the variables, all the values of internal pins and all the values which are inside this test bench. So, we give it the name here, and anything which is the variable where the variable lies inside this module name, that will be saved. So, here we are writing test bench, it means in this test bench and whatever module it is instantiating, all the internal variables will be saved. If we specify a particular name here, then only those variables inside that module will be saved. So, here we are saving everything. We end this initial module and then we end module this test bench. So, this is the test bench which we have saved. Now, we need to simulate this test bench and full adder using our iVerilog tool. So, we go to the command prompt, we type iVerilog -o, this is for output and we need to give a name, let us say full adder. This is the output file name where the log will be saved of this execution. Then we need to specify our test bench, which is full adder underscore tb, and we need to also specify the module which is full adder. This is the command to execute. So, this is simulated. Now, we write VVP and the file name full adder, which we have given here. So, this is the truth table which we have simulated. Now, we need to cross check whether this is matching our results. So, we see for the value A000, which is the first line, the sum is 0 and carry is 0. So, this sum and carry, this is correct. For the second line, 001, so the sum is 1, carry is 0. So, this is correct. For the third line, we have 00010, sum is 1, carry is 0. So, this is this third line, this is correct. Fourth line is 011, sum is 0 and the carry is 1. Again, if we see the fifth line, which is 100, so sum is 1, carry is 0, this line. For 101, we have output 0 and 1, this. For 110, output is 0, 1, this. And for the last variable 111, sum is 1 and the carry is 1. So, this is exactly what we have figured out using the circuit. So, this we have now simulated using iVerilog. We can design any circuit like this in iVerilog. Now, we want to see the output waveforms. So, we want to see these results in terms of waveforms. So, we write GTK wave and the name of dump file which we have given here, which is full adder underscore VCD. So, this is our test bench, and this test bench is inside calling one module, which is add1. This is the name we have given to that full adder module. This has these inputs and output A, B, C, C out and C and sum, and it also has those inside the internal nodes which we have given 0 to 4 value. So, let us select all the signals and insert it into the signal window. So, here we have these A, B, C in, C out and sum. Now, this T, which is an array of variables, it has 5 variables 0 to 4, 0, 1, 2, 3, 4, it means it has 5 values. If we double click on it, this opens up all these inside variables T0, T1, T2, T3, T4. So, first we need to check whether the output signal is matching the expected output. So, for 0 0 0 sum is 0, carry is 0. So, this is first stage, this is second, this is third, this is fourth, this is fifth row, sixth row, this is seventh, and this is eighth. So, there is a just starting of that eighth row, but simulation ended here because the signal is applied, and after that we do not wait for next couple of time units to see that waveform. So, if we see that signal is raised here, but it is not shown as a step because the simulation ended right here itself. So, to avoid this kind of problem, we add one more stage here. For example, the first stage 0 0 0, that vector we again add in the test bench after all the 8 lines. So, there will be a 9th line which is repetition of first one, then we will see all the values comfortably. So, here now we have these 7 lines and the 8th is kind of not shown here because of the simulation ended right after application of signal. So, we can look at these waveforms and cross verify with our truth table whether these waveforms are correct or not. Wherever we are going to click, that will show the input output values here in this signals window. One more important here to point to note here is, in this circuit we have assumed a wire. For example, here we have written assumed internal wires which is T, and we have specified the value 0 to 4. It means 5 internal wires we are assuming here. However, inside the circuit if you see, we are using only 3 wires. For example, T0, T1 and T2. We are not using T3 and T4. These 2 wires we are not using anywhere in our module, but we are instantiating those wires by using this wire 4:0 T. So, these 2 wires, these are extra to our full adder. These wires are not used inside our module, but we have instantiated it. That is why if you see in the waveforms, these T3 and T4, these 2 wires, these are shown as Z, or the state of these wires. Anywhere if you see, the state of these 2 extra wires is shown as Z, which is a high impedance state. However, for all the other signal A, B, C, etc., the value is either 0 or 1, but for these 2 wires always the state is high impedance state. So, these 2 wires which are extra to these modules, these wires are not connected to any of the logic gate, and no external circuit is driving these wires. It means these wires are dangling and they do not have any finite value to put there. So, the term is high impedance, we call it, and we specify that by Z. So, here we see we have Z impedance state for all these dangling wires which we instantiate, but we do not use it inside our circuit. So, Verilog is different than normal programming languages in this way itself. In normal programming languages, we consider state as either 0 or 1 if it is a binary state. However, in Verilog, a state can be a 0, which is binary 0, a binary 1, or it can be even a high impedance state, which is possible actually in electrical circuits. If we talk about, let us say, the output of a certain gate, At some point it may be possible that pull up network is off and the pull down network is also off. So, if pull up is also off, pull down is also off, there is no network to drive the output that time. So, this output node is not driven by any of the gate or any of the transistor. This does not have a low impedance path to supply or ground. So, we call it the high impedance state, and in this state if anything, any other circuit is driving this output node will assume that value itself. So, this high impedance state, if we drive this using a very low pull up network or external pull up, this is also possible in certain circuits. We put certain weak pull up networks to avoid this high impedance state. This high impedance state is not desirable because now the output is not driven by any of the network, not pull up or pull down. So, this output can take off any value which is not fixed by our circuit, and this dangling value or the high impedance value, if it is going to the gate of another logic gate, that logic gate will not be able to predict whether it is a 0 or a 1, it can be in between. So, if the input is in between somewhere, this is going to create the short circuit current in the next state. So, these high impedance states, these are not desirable in digital logic design. So, wherever we see a Z state that is shown here by Verilog by this yellow color, it means that there is a problem somewhere. So, this is also shown in this variable where we have shown this waveform as red. However, if in the test bench, if we just remove these extra 2 wires, or we start the wire definition only from 2:0, then these wires will not be there and there will not be any high impedance state. So, apart from that, the circuit is working fine as per our expectation. So, this is the full adder we have developed using Verilog. Let us take one more example. For example, we want to make a 4:1 multiplexer. So, let us see how we can make it. So, let us take one more example, which is multiplexer. This is also very widely used circuit which we develop in Verilog. Four is to 1 multiplexer. So, what is a multiplexer? We have a module which has 4 inputs now, because we are developing a 4:1 mux. So, this has 4 inputs, let us say I1, I2, I3, I4, and the output is only one, which is, let us say, out. So, this block will pass only one of the input to the output, and that selection is dependent on 2 selector lines, which is, let us say, J0 and J1. So, these are 2 selector lines. By these 2 selector lines, we can select which one of the input will pass through the module and go to the output. So, depending upon value of G0, J1, which are all the binary values, we can select either I1 will go to out, or I2 will go to out, I3 will go to out, or I4 will go to out. So, this is the multiplexer which we want to make in the Verilog. So, let us see the code. So, we again go back to the bin and make a text file. This is mux 4 to 1, and the extension is .v. So, this is the file. Now, we write the module, we give it a name mux 4. Here we are defining input pin which is of type wire, and it has index 0 to 3. It means there are 4 variables named I. So, these are our I0, I1, I2, I3, what we have just taken as a input to this mux. Then we have two selector lines. So, we write input wire type J0 and J1, and our output wire type, let us say O, and then we close this definition. We assume some extra internal wires which is 0 to 1 S. Now, we assign the value to S. This S is J1 J0 1 tick B1 J0 1 tick B0. So, we are assigning the value to S. This is a conditional operator now. So, what is a conditional operator? Anything which is before this question mark, if this is true, then the next code will be executed, whichever is immediately following this. It means this, and if this is not true, this J1 is not true, then the next block will be executed. This is very similar to the statement if then else statement, which is used in most of the languages like C or Perl or any other language. We have the if then else statement, conditional operators there. Similarly, we have in Verilog here, which we can write like this. Then we assign output to if S is 2 bit of 00, then we want to assign I0. So, we can write it first, then we will explain what it is. So, here we have written assign statement that we want to assign the value to output. Which one of the value we need to assign, I1 or I2 or I3 or I0, that depends on the value of selector line, which is now 2-bit vector or 2-bit variable. So, this is again if then else statement. If this value is true, it means if the value of S is 2 bits, which is 0 0, then I 0 will be assigned to output. If not, if it is not 0 0, then it will go to the else statements. Else is after this column, whatever is there, that is else for this block. Now, we go to this in the else statement, else it will again check value of S. If this is 0 1, then I1 will be assigned to output, else again it will check for value of S. If it is 1 0, then I2 value will be assigned to output, else if the value is not 0 0 or 0 1 or 1 0, then in rest of the cases, which is 1 1, the I3 will be assigned to the output 0. So, this is how we have written the code for this 4 to 1 mux. After this, we write the end module to close the module. So, this is the Verilog code for the mux. Now, we need to write the test bench for this mux. So, we go to new file, make another text file, which is mux 4 to 1 underscore test bench, and extension we need to change to .b. So, this is the test bench which we can write. Similarly, what we have written for earlier cases, we write the module as test bench and define all the possible values of selector lines S0 and S1 and the values of I0, I1, I2 and I3. So, this is very similar test bench. Now, we want to simulate it using the iVerilog. We go to the command prompt, we write iVerilog minus output or hyphen output mux 4 by 1. Then we give it the test bench file here, which is mux, this one, and the module file, which is mux 4 cross 1. dot v and we simulate it. So, this is simulated now. We can check the output in text form by VVP command. We give it the name which is we have given here after this minus O option. This is so this is the output when I0 selector line is 0 0, the output is 0. When selector line is I is 1 0 0 1, selector line is 0 0, the Y is 1 and so on. We can see the waveform by mux 4 underscore test dot vcd. So, when selector line is 0 0, then output Y should follow the II0, which is the first vector, the first variable II0. If S is 0 1, then it should follow the second one, which is this variable. First it is 0, then it is 1. So, the output is following this one. In the third case, when the S is 1, Y S0 is 1, S1 is 0, this case it should follow, the output should follow the II2, which is this input. And in the fourth case, when S1 is 1 and S0 is 1, it should follow the I3, the output should follow the II3, which is following here. This is 0, then output is 0 when II3 is 0, and this goes high when the input II3 goes high. So, this is how we can simulate. So, today we have seen two very important circuit. One is full adder, which is very widely used for digital design, and then we see the mux. The mux is also very important circuit which can be used for selection out of inputs, many inputs. We have, let us say, 4 inputs and we want to select one as a output. So, we can use mux in digital circuits. We saw that we generate the Verilog code, and when we simulate it, one is the textual format where we generate the truth table. That truth table we can visually check by the circuit, or we can see the output waveforms using GTK Wave, which is again a free software. This visual waveforms we can see and cross check. This waveforms are very much useful if we end up with some problem in the code. So, it is very easy to debug if we punch all the internal nodes, and if there is a problem, we can go one by one from the input to the output, and we can figure out which signal is not matching our expected results, and that portion we can again go back to the code and see if there is a problem in the code. So, these are some of the circuits we can easily simulate using Verilog. For practice, you can simulate some more circuits. So, that is all for today. Thank you.